So good morning, ladies and gentlemen. Welcome to a hands-on demonstration, rather different to my previous talk. And I'm going to show you some stuff. I'm going to show you the result of what I did with a small application for a client and some optimization and tools for doing optimization. This is going to be in Linux and C++. So I'm going to give you a little bit of background about that one. We're actually going to see real code and 6, 7, possibly more variations on this one as I went through. So this was a real application that I wrote for client. I want to show you different versions and how I optimized it and how I used the tools to guide that optimization. So I'm going to be using valgrind and cachegrind. I'm going to be using the perf record and report, perf stat, some bit of strace, a few other things, and some compiler explorer to have a look inside what's going on and to help me guide this one, and some basic things like bash timing. So that's how to interpret that one, and some things about library. So here is the client problem. So this particular client has got an IBM mainframe. And for those of you who are less than about 150 years old, you may not realize that there are machines in the world that don't use ASCII. So IBM mainframes use an EBCDIC character set, extended binary coded decimal indicator code or information code. So remember that BCD thing, because we'll come back to it. And what they got is that they got COBOL files, lots of them, big ones. And they want to take these ones here, they're in binary formats, and they wanted to translate them into CSV files so they can put them into their data warehouse. And they were looking at a disaster recovery situation. So what do we do if the mainframe's not there? And so they got an issue here where speed is important. Because you're in a disaster recovery situation, your business is basically stopped. You want to get running as fast as you can, and you've got hundreds of gigabytes of data to process. What are you going to do? Well, you wanted to go fast. So they went, help, help. Right, so I quickly hacked up something, and they went, oh, no, actually, we need it to be configurable, because you know the 3 versions we gave you? We need more than that. We've got about 100 or so different formats. We need something configurable. So I went, okay. They had found on the internet an open source C# tool, and they got this one and downloaded it and tried running this one, and it took about 11 hours to run on a 2 gigabyte file. And I went, I don't think that's very good. I'm amazed at how slow people can do that one here. So I thought, right, okay, let's get some C++ out here, even though they're not a C++ house. Let's do this one. They wanted to run this on Windows rather than Linux, but portability is very good between these things, apart from one part which always catches me, which I'll mention later on. So standing back from that, performance. What is the right approach to doing performance? You could kind of get in there and go, oh, let's just play with things. Well, you basically kind of need to understand the story of how performance happens. And you go, well, okay, well, I start at the top here and it's too slow. So I start profiling it and you're looking at this. And then you stop doing the silly things. Stop doing unnecessary stuff. Stop doing things like I/O if you don't need to do that one, or lots of little I/Os, and see if you can make bigger I/Os. See if you can get rid of network stuff, system calls, all those other kind of things, because they're the big, heavy, slow things. Get rid of exceptions, get rid of other parts like that. Once you've got rid of that, the things that cause orders of magnitude slow down, then you can start saying, right, okay, now, what you'll probably find when you profile is that what comes up at the top is now memory allocation, mem copy, and memory comparison, and string stuff. That's usually what happens at this point. You go, okay, we get stuck into strings. Temporaries, all those other kind of things get in your way. Right, okay, so we can deal with move semantics and other things. In this particular case, move semantics isn't an issue. This one is quite well focused. It's not like other applications I've looked at, but it's a real application. I wanted to show you real stuff rather than just made up stuff. So once you've got rid of that and basically got your memory allocation under control, you then go, right, now we can do different algorithms. Now we can start working about data structures and lookups and other things, and order log n and order n, order 1 and hash tables and things, and working out what actually needs to be fast, because you need to make certain things fast and other things probably will end up going slow because of it. And then, and only at that point, is it really worth starting to worry about memory bandwidth. because you're now dealing about data layout and cache awareness and all those other kind of things. So we're sort of kind of going to go through this story because you always have to go in this order. There's no point in trying to mess around with compiler settings and cache-aware programming if you're doing lots of disk I/O. So it has to go in that order. Here is a nice little chart here from Sergei Ivanchenko. I borrowed this one because it was just pretty rather than rewriting it. And this is about the different types of operations and their relative speed. Now, the horizontal axis is logarithmic. It's orders of magnitude. Right at the top, you can go register, register, add is less than 1 cycle. It's really fast. We got lots of nice fast stuff up the top there. Memory writes, etc., are quite fast. That because of the store buffer. We've then got all the things about branch predictions, taken and not taken, and L1 cache versus L2 cache. The surprising thing when you look at this actually is that you find out that square root is faster than division in certain cases. You've got all the stuff about vectorization and function calls, everything else. Basically, the thing is down the bottom here is the really slow stuff. This is orders of magnitude nice and slow. This is thread context switching, C++ exceptions, or throwing and catching of those ones, context switches, kernel calls, memory allocations. Get rid of those. Those will all slow you down horribly. So I thought, I'm not going to bother with threaded code. I'm not going to bother with exceptions, and I'm going to avoid all my system calls where possible. So that's just to give you an idea about this one. By the way, notice this is orders of magnitude. If you throw multi-threading in here and you get perfect scalability, big if, you probably can move yourself 1 order of magnitude to the left. 8 cores, 1 order of magnitude to the left. Get it wrong, and you'll go 2 orders of magnitude to the right. Yeah? So notice that multi-threading is not going to save you here. It's not going to make the difference between the bottom right and the top left. You need to get your single-threaded programming going fast first before you then get some linear scale-up with the other ones, because you can get 3, 4 orders magnitude of difference just by programming correctly. Okay, let's look at some tools. What tools might we have? Well, you can run tools on unmodified applications, so there's the whole perf set of tools that you can use on the Linux. There's older ones like OProfile. Top is just will tell you that it's burning CPU. It doesn't actually tell you that much, but it can tell you whether you're CPU bound or not. Are you waiting for I/O? You've got I/O top, which will tell you which processes are doing input and output. VM stat, I/O stat, well, fairly gross. And bash time. Bash time is actually, in this case, I'm going to use that quite a bit because I just want to know what the runtime is. I'll need other tools to tell me why and what to do, but it just runs faster or it doesn't. These ones are full speed tools. You can run the thing at full speed, not a problem. But they may, based on sampling, so you may get sort of kind of plus or minus some stuff. So it's an indication. A lot of these things aren't going to say, here is the big problem. You have to learn to interpret the output of some of those tools. There are commercial ones from Intel as well. You can modify your application. So you can use gprof, gcov, things like that to try and do that one. You can put in timing using stdchrono. Boost has a CPU timer, etc. So you can write your own instrumentation. You can also use simulators, and I'm going to use that at some point. I'm going to use cachegrind. They're slow, but they give you very good insight. How do you use these ones here? So here's some stuff about how to do that one here. My favorite sort of compilation options are usually -03 and March native. So 03, most people go, use 03, it breaks my code. And I said, well, your code was broken. It just told you that it was broken. So 03 should not break valid code. And march equals native. This says compile for the architecture of this machine. If you don't do that, it will then compile for an i686 from about 15 years ago. It takes the lowest possible, compile for anything that can work on any chip. You usually don't want that. You usually want to say, I've got this chip, can I use it, please? We could use valgrind directly for memory allocations. In this case, we're not doing many, so I'm not chasing a lot of memory allocation stuff. But I will be using cachegrind. There's cachegrind and callgrind. They're similar, but not quite the same. Both of them will do branch simulation and cache simulation. Cachegrind is a little bit faster. Callgrind has got some extra stuff that will actually tell you about how much memory you've used when you've loaded it and how much of a cache line. There's some annoying differences in the command line options as to whether it takes an absolute path name or relative path name. Go and look it up or ask me about it afterwards. And the strange grep at the bottom is because the annotation one starts printing out horrible things when I did this one here. The thing about cachegrind is that you run your program under this one, you'll get some summary information, and it's producing an output file. In this case, the output file I called chg.out, and that contains a lot of information. You then use a tool to interpret that, CG annotate, and this will then give you line-by-line information about your program. So we're going to see that. Right, let's go and actually have a look at this piece of code. Well, first of all, let me describe what I've got here. So I've got oh, where did I go? So this is the problem space. I was given a COBOL copybook. So this is what I was given. This is actually some COBOL. Don't worry. I know it's all uppercase and got dots and things like that. This is a COBOL data structure. And it tells you things like, it's basically a structure definition like you'd see in C or C++, but with some odd things like, so all these pick things at the end tell you S9, it's 4 bytes long, it's computational value, it's X10 or X02 basically says it's strings. So I've got 3 types of things here. I've got strings, which need to be trimmed, because these are all fixed widths, I need to have output. I'll show you the output in a moment. I've got some integers, which are stored in the opposite way round to Intel chips, so they're big endian, not little endian, so I have to reverse those. And then I've got binary coded decimal as well. When you split this one up, you actually get this. This is what the structure of the output looks like. So I'll show you what the output file looks like in a moment. So that is essentially I want to produce a CSV, or in this case, pipe-separated file that looks like this. So I take the binary file and I get here, I've got a header row. It's got pipes rather than commas, and then lots and lots of these bits of data after it. And all the strings will be trimmed. So that's the problem space there. What does the input data look like? Well, the input data looks like this. So here's the first 400 bytes. What's that look like? Okay, so that's a whole bunch of binary. Let me just realized I've forgotten to. EBCDIC. So here we go. Here's an IBM specification that says, right, here is how characters are represented in EBCDIC. This is not going to be a lecture on this one. It's just to do this one here. Notice you've got all the characters. They've got some weird characters, and 0 to 9 are all over there. One of the odd things about this is, if you're used to ASCII, you will not. You will go like, huh? Why do they do that one? Is that A, B, C, D, blah 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 goes down to I, and then it's a bunch of characters, and then it starts again at J, as they're all sort of kind of 10 apart. So they do sort of 10 letters at a time with gaps in between. They don't have A to Z as contiguous characters. Okay, fine. Well, that's what I've got. I need to sort that one out. So I hope that you're sitting there thinking like, right, so how would I do this? How would I do this? How am I going to do this in an efficient way? If I can't, because I've got all these sort of kind of disjoint characters I need to translate, and then I'm going to have some of this BCD stuff where it's got 2 characters inside one thing. Oh, that's a bit horrible, really. Well, so you look at that as a hex dump and you think, what's going on? And then halfway through the project, when you've tried to decode that by hand, you actually find out there is a magic option that says, please use that as EBCDIC, and you go, oh, thanks for that. At last, I can read this damn code. Oh, look, yeah, I can see that one. I just need to pull that out. Right, okay, I can see 1, 2, 3, 4, ADC. I can see how that is. So once I'd found that, life was a lot easier. Okay, so that was that. Right, how do I deal with this one? Well, let's have a look at what I created was some. So I created a JSON file that had these things in it here, and I said, right, okay, I want to have Here's the field. Here's the offset in the file. This is how many bytes it is, and here's its type, string. Okay. Yes, they did. Some of these ones had got commas in the names, which threw me, and I thought I gotten off by one error. No, it actually was the one that they gave me, and it really did do this one. That's really annoying. Lost some time spacing of that one. Anyway, so that was 5 long, this was 7, etc. So I've got all this one here and basically describes the input. Right, okay, so that's what that is. Now let's have a look at my first version of the code. So the way I decided I was going to do this one, does that actually fit on the screen, all of that? You're not truncated or anything? You can see that? Does it need to be bigger? Okay. The way I decided to do this one here was actually ended up a single file. I was going to use a JSON parser from the N-Loman JSON parser, header only, because this was, I was giving this to a bunch of people who were not C++ programmers. I didn't want to install anything. I said, right, okay, here's a source file, here's an HPP file, and just stick this in Visual Studio and say compile. I decided much way was to use a translation table from MCDIC to ASCII, so that's what I got, a translation table there. Reads the configuration in. Let's go to the bottom of the program. What does it do? It's very straightforward. Look at the arguments. I just provide I want the input. So I want the configuration file, first argument after the program name, and an input file. In this case, I'm just checking it to standard output. This should be relatively straightforward. I mean, the entire program is only 155 lines long. I'm not going to do all of it. So reading configuration is just going through. This is really nice, and go just read the JSON, please. Do that one here, and then just pull out the fields. Nice, very straightforward. Printing header rows, yeah, well, that was that one here. And this is where we start actually to meet the real world of stuff. Process. I've got an input stream. What am I doing? Well, they're all fixed length records. So that's fine, and I just go and read from the input a fixed length record into a buffer like this. And then I just got to go through all of the fields. So I'm going around all the fields that were in that JSON file, go and pick out the right thing. If it was a string, then call string and write that out. If it was an int, then parse the int, parse the decimal, do the string, go around. Nothing too exciting. You probably would have come up with something very similar yourselves. Let's see what that turns into. This is the unoptimized, my first go at this application. Right, okay, so I need to do this here. The 40s are spaces. I should probably think that I wrote this in a hurry. I could go on refactoring. You will see some refactoring as I go. Anyway, so while I'm not, this is saying, right, I want to get my string like this. How long is it supposed to be? Work backwards and trim the string that way. So I'm trimming the string and then translating it through the table. If it was an integer, I have to reverse the bytes because they're the wrong format for Intel. The decimal one gets to be a bit more exciting because the decimal is packed decimal. So what you'll see is, I'm not sure if I've got a decimal in here, but what you will see is 0102 would actually be 12. So it's actually a byte at a time. And then the last one, there will be the last nibble, so the last 4 bits will be C or D. C if it's positive, D if it's negative. For any of you who will work that one out, you go, okay, these guys do accounting, that's credit and debit. That's actually hardwired into the way that IBM arithmetic works. Okay. And that explains why I'm doing some bit shifting here to take top 4 bits and bottom 4 bits and multiply the top ones by 100 and other things like that. I'm doing it a bunch at a time because I need to take the top 4 there, do some shifting, and then I do some printf. So I just print out the floating point number. Right, okay, that's that. So let's compile it. Is that going to be off the bottom of the screen if I do that? Maybe, is that better? Because a lot of you will, I think you'll probably just be going like, wow, don't see anything. Right, okay, so now let's time this guy. So I'm going to, oops. No, okay, let's, I've got some very big files and some small files. I'm going to, let's try the, so this one here is Let's time that one. That will take about 10 or 11 seconds. This is my first go of this one here. Notice it's piping out. Okay, let's see what that actually looks like. That was 10 seconds. Okay, right. Which, if you look at this one, ls minus l of the actual file itself. So here's the input file. You'll see that's really quite large. So if you want that in thing, it's 191 megabytes. So it's on 191 megabytes in just over 10 seconds. It's on my laptop, which is a Core i5. Well, that's something not doing too badly. So what other things could we look at? Well, let's find out what it's doing. So courtesy of Michael Kereski in the front here, I'm doing an S-trace C on this one to count all the system calls. Picked that one up this morning. It's worth going to other people's talks, isn't it? Find out what the hell this thing is doing. How is this talking to the operating system? Remember I said, let's see what system calls do, because they'll really slow you down if you get that one wrong. And this gives you a lovely printout like this that says, aha, look, 70% of the system calls there, this one here, are calls to write, which is not really surprising. It's writing a load of stuff, it's reading a load of stuff, and then it's got some sort of kind of open and close things, etc. It's basically doing reading and writing. So I'm not doing anything really silly that, other than, okay, I've got 200 megabytes and 24,000 calls. Okay, so there's something in there. Right, so that's one look. Let's have a look at so that's what perfstat would tell us. Perfstat, run that on here, the same thing. We do go fast on this one. This just happens to be the slowest one. And that's now going to give us, so perfstat is looking at some of the Intel performance counters and says, well, okay, it gives us some interesting information. It says, right, okay, you're running at about 2.2 gigahertz. Which is, so this, interestingly enough, as we go on later, that number goes down. It tells you some things about stalled cycles, which is how much is it waiting for stuff. I'm already at 2 instructions per cycle, which is really very high. How many instructions is this thing executing every clock? Jason McGuinness was saying he reckons 0.7, 0.8 is probably about what most applications are, and they struggle to get beyond that one. So I'm already in really good territory here about that one here. The other one is this. Stalled cycles per instruction. Most of the time in applications you're waiting for the memory. This is saying I'm really not waiting for memory that much. I'm hitting the CPU quite hard here, and the branch prediction is not bad. Okay, fine. Right, so that's perfstat. I could also then say, well, let's have a look at let's actually do, whoops. That's -C, you shouldn't let me do that. So this is then a sort of standard profiler. It's an external one, you can just look at stuff, it's nice and free, and then we'll show you where it's spending its time. And so perf report will now give us something like this. And this shows us inside. Now, where are we spending our time here? Well, okay, so the first thing is stream insert. Oh, okay, I seem to be doing I/O. This is then my process, and then I've got writing and printing and divrem. Oh, that's going to be all that sprint and the percent whatever. That's probably not so very good here. A lot of excess put-n, so that's output, some string stuff, some printf. Sentry here, by the way, these are the items which are created by I/O stream. Memcomp. That's always you end up with memory allocation and comparison somewhere. So this is memory comparison. This is doing string comparison. String length, unaligned, memcomp. This is not untypical for sort of kind of first pass application. You look and you go, I've got quite a lot of things that's spending its time. I'm spending too much time in too many different places, and none of them are really helpful. Okay, right. So that tells me I need to sort of kind of look in some of those areas. I probably need some finer grained stuff. Right, okay, let's have a look at... so here we go. I'm not going to run it on the full size thing because that will kill it. That will kill it because it's much slower. So I'm going to use something that's a lot smaller. So they did give me some test files, so which is nice. So I could actually run this against... and this particular version was using directed output. Okay, so what this one? Valgrind, and I'm using the cachegrind tool here, and I'm going to simulate branches So do the branch detectors, branch simulation and cache simulation, but it only does a two-layer, L1 and last cache, produces an output file, runs what I've just got there, and they are, yes, okay, fine. So this is, so that's cachegrind. I've run it on a much smaller file on something that's less than a megabyte or so. And this is what you'll get to start off with. And so here's some stuff. Instruction cache misses 0. Great, that's good. You don't want to have those because they're absolutely mean. But data references here, these numbers are sort of kind of worth looking at, but they're not as much fun as annotate. CG annotate, cg.out. So give me that file I just had there, and I can say annotate a particular file, or I can just say auto equals yes. It says go on, automatically annotate any file that looks like it's worth dealing with. Right, this is what you then get out of cachegrind. So there's some important parts to interpreting this one. It says, yeah, I've simulated a 32 kilobyte cache. It's using a 3 megabyte L3 cache, because that's what's in my laptop here. It's saying, here was the command line. Here are all the events that it's doing, which we'll go through in a moment, and there's some thresholds. You can cut off some noise at the bottom. The important things to look at this one here is I'd probably first look at this line. Let's see if we can interpret this. So I've got some stuff about instructions, and it goes 80 million instructions, 2,000 misses. Yeah, I'm not worried by that. That's fine. If you've got instruction cache misses, sort that out first, because that will absolutely kill your machine. If your machine doesn't know what to do, bad performance. Here, next one, data cache, 24 million data reads. And D1 MR is data cache 1 misses for read. 16,000 and 8,000 of those then went out and then missed the last level cache as well. So this thing is pretty cache friendly actually, which is what the numbers we saw with that first one was. So 16,000 out of 24 million. It's really cache friendly, which is why I can get that high throughput. Same for writes here. It's actually not doing much in writes, not doing much in the way of write misses. Writes have to do a read before a write. Here is the branch simulator. 11 million branches, 0.3 million mispredictions. So this is using a simple branch predictor. If you remember back to that big thing of fast and slow, branch prediction misses are 10 times slower than correctly predicted ones. So this is, branch predictions are good here. So that's what branch conditional. There's also branch indirect. And this is then this is basically virtual functions or call through a function pointer. So call square brackets. And it simulated that, and again, that's fine. So this basically tells me, this is pretty good, I haven't got instruction cache misses, and my data cache is working. Right, okay, let's have a look at the rest of this, and this then gives me a similar breakdown to the profiling, but this is now inside. I can see there's a lot of fwrite and strings, etc. Okay, what's really nice about this one, it says, right, okay, here you go. I'm going to show you on a per line basis where this is happening. So if I've got things around I'm talking tens of millions, we can see what's happening on here. This is all the library. I said, just tell me anything. This is actually showing me in the STL where all my time is going. Not much, not much, not much. Okay, there's some stuff going on here about string construction. Yeah, okay, let's see what we get that. Some more string stuff. Let's move down here, because if I go out of that and just say, look, let's have it was a V1, wasn't it? So if I do this and I'm going to say, look, okay, just show me my program. So I can say, trace this on an individual program basis. And it gives me line per line basis. And it goes, okay, right, here we go. So we can see hundreds of thousands around this loop, which is not surprising given the number of things I've got here. Oh, look, here we go. This is where all the fun is. So we found our sort of kind of hot loop here, which is this translation loop. And also there's this loop here doing that one. Okay, so there's a lot of stuff going on there. This is showing me hot in the middle of my program. So it's all strings. So it turned out that I'm actually processing strings, not many integers or decimals at all. In fact, there were no ints in that file whatsoever. But there were some decimal ones, but I didn't have many of them. So it's surprising I had all that if div, etc. Right, okay, so having done that one, I mean, okay, we've got too much fun with that. Let's go and see what the changes were. Remember, there was a lot of I/O going on, so let's have a look and see what the changes I made for the next version was. Same kind of stuff. I went, well, okay. I was doing some stuff around here. So what have I done here? I've decided, actually, look, there was a lot of string comparison going on. There's that memcomp. That's string comparison. It was doing memcomp SSE4. I'm going, okay, there's something with string comparisons. And I went, yeah, you know what? Look, every time I was going around here, I was doing an if string equals this, if string equals that. And I'm going, hold on, why am I doing string comparisons here? What I need really is to be comparing against an enum or an integer. Why am I doing string comparison of something this big? I have to go all the way down when actually there's only 3 choices here. Well, okay, let's create an enum. So I've got an enum of those ones here. I've got some way of converting that, take those if statements, convert them into the enum here, and I then do a get field type on it here when I'm reading it in. So instead of storing string for this one, I'm saying I'm storing an enum, which makes this now tests against integers much faster. Okay. Notice I was doing a lot of I/O, so the first thing I went, oh, look, I'm doing I/O or C out on every string and every separator, and I'm going like, oh, this is kind of, that's why I'm doing a lot of this. There's a lot of this stuff on I/O and on the iStream. So what I did instead is, right, okay, let's create a string, let's reserve the size of that string, and then just do an output on that, do plus equals. So get these things here, instead of returning a string by value like that, I'm going to get it to build it up and then return it as 1. So this is still doing string and string addition. But here, so it's fairly similar. But instead of doing, I'll start at the end of the string, go backwards, and then translate these ones and do that one here, I said I decided I was going to be clever, because I'm always deciding I'm going to be clever like that, and I will work out as I go through the string what the last non-string character was. So I'll do single pass, because that's going to help, isn't it? And that was most of the other ones. So that was my first attempt at changing that one here, and you can see it's storing field type rather than string. Let's see the difference. So, plus, plus. So let's go to V2. Ding, ding, ding. And let's run that instead. And that now takes, instead of 10 point something, it's now 5 point something. So it's twice as fast. Yay. Let's try, let's see where it's spending its time now. I would use perfect record for this one because then I can use this full-size file and not because it's 20 times slower if I use valgrind, cachegrind. But it tells me exactly what's going on inside. That's what's really nice about it. Thank you. And hey, now, the top of the line here, guess what? I've actually got my program at the top. I'm not wasting time in the library. It's actually in my one here. It's still only 22%, and I've still got a load of printf and divs and and still a load of string stuff going on. But I've got rid of part of that one. Okay, so these are the main things here. So obviously the printing and the comparison there is something I have to deal with. Right. Okay. So what's my next trick then? That was version 2. So where did I go after that? Well, let's have a look. So having done that one, I went, right, okay. Conversion of decimals. Having gone through this one, I did actually go through into a cachegrind and found out that there's quite a bit of decimal stuff going on that big file. It takes minutes to run, but I'm not going to inflict that on you. So what do I do here? Well, I went, okay, so I did some stuff and I went, look, this string stuff. Why am I doing strings here? I should be, strings are sort of doing all this business about, creating things and small string optimization. It's a string buffer, it's a buffer, yeah? Okay, so I went back down to the good old-fashioned straight array here, so back down to C-style processing in good old star pointer plus plus, yeah? guess what? That's what the machine supports, so that's going to be fast. So having measured that, I've got down here, I've now changed this one, so I'm now returning the new pointer, passing in where it needs to go, and you'll see here I'm actually writing out into, I'm doing the spaces here and trimming here, and I'm not returning a string anymore. I'm doing the write inside here and just saying how many I've got so I can bump the output pointer. So I've replaced the output with strings and just gone straight to that one here. Okay, right. So same for integer here, saying this is just writing it out, and I'm just doing an sprintf, having reversed it. The decimal one, I went, well, actually, I seem to be spending quite a bit of time here. So having gone into this one, I sort of kind of looked at it and went, most of these decimals actually don't have decimals. They don't have any .00. Some of them are prices, 32.99, but a lot of them are actually just whole numbers. So actually I worked out that it was going to be faster to say, look, I'll just print it out like that without these decimal places. So I did a bit of timing measurement, and that's where I ended up with that. I also said, well, okay, this business of output on the shell, so I was chasing down why, how could I get rid of some of my I/O speed? So I went for a 4-argument, not a 3-argument version. Also, I was having lots of fun with this one, and Windows helpfully decides that Control-Z inside a file is end of file, which is really helpful because it assumes it's text mode, so I had to put binary mode in there to stop it doing that one. And notice I've redirected the output using freopen. Now let's have a look at. There we go here. This becomes a relentless thing. You get kind of addicted. So how much faster can I make it go? It's fun. So we'll get some of the way down here. So and that one now needs to have that removed, and it's now. Hey, I'm speeding up by a factor of 2 again. Yeah, okay, we're cooking on gas now. We're having some fun. That's a strange English expression, don't worry about it. So let's see where that one might go. Ah, right. So 32% inside my thing here. We can actually see if you go into this one and annotate it, goes, okay, here we go. You can cycle through all of the the instructions where it's spending its time. And it appears to be spending most of its time in this translate loop. And there's also doing some if out here. Okay. Interesting. See, here's a conditional move instruction. So it's actually avoiding a branch by doing a conditional move. So the compiler's quite good at this, but it seems to be spending most of its time in this loop. Okay, right, so, and there's another one here which is doing if field count separator. Oh, actually, I seem to be doing a lot of stuff on this. Really? Okay, so I go around that one, and but it tells me that's where I'm spending my time. So, okay, I better do some of that. So where do I go after that? I will, as I said, I could go into all of the line-by-line cachegrind stuff, but what do I do after this? I decided, okay, so what was my next trick? So my next trick was to say, right, it seems I was spending time in here. I seem to be spending time in the decimals. So I spent a little while going, well, maybe I can get rid of this kind of printf, because I'd sort of kind of done something a little stupid. Does anybody recognize what I've done as being stupid? And it was one of those, you idiot moments. What I'd done for the decimal is I'd gone, right, okay, I picked up this decimal, I've reconstructed into this thing here, and then I print it out. So I'd taken what was already split up into digits, turned it into an integer or a floating point number, and then used printf to turn it back into the same structure. Why did I do that? That was just a silly thing. It's already in a 0, 1, 0, 2. Why have I taken those ones, undo all this multiplication just to undo it? That was silly, wasn't it? So instead of doing that one, why don't I just say, well, okay, look, that was, pick that nibble up and take this byte here, if it's 0, 1, 0, 2, shift it like that, 0, 1, and add on the 0 for the ASCII, and then do the bottom one here. So that basically is what I need to do in order to print it. It's like, I just had spent a whole pile of time converting between BCD into decimal, back out into visible BCD. I got to do some stuff here to get the last ones and the points in the right place, but Yeah, okay, fine. I had been a bit silly, so it was one of those "you idiot" moments. It does happen. Evidently, it does. So, so what are we getting now when we do that? So that's v4, 1.92. We're getting somewhere here. Okay, so you can see little by little, you're just sort of chipping away, and you're taking off, in some cases, a factor of 2, in other cases, a little bit less than that. Right, okay. 54% in my process here, and not in the libraries. I have an interesting question as to what this part is. Is this one here, which appears to be saying, it says unknown, doesn't know where it is, it's labeled as K. I think it looks like some part of kernel stuff, and this 0xFFF, it's way up there. It looks like it's part of a library or something similar that is in kernel space. I'd be very interested if somebody could tell me what that one is. But notice, I've still got some strcpy and some memchar and memmove and some string stuff going on. So do I only need this in put s and string? I can probably get rid of some of this as well, but if I go into here, where am I? I'm still in my thing here of spending a lot of time in this translation loop. Okay, well, what do I do about that translation loop? Yeah, it's most of the time is there. And some char traits, etc. So it just gives you a very good idea of where things are. You can just, without having to do a lot of work to find out what's happening. Okay. What was next after that? Having realized the error of my ways, I thought, well, maybe I can do this with some, I had got rid of this BCD to binary decimal thing here, and now I'm going, okay, separators, string fields, what did I do here? This particular one is right, okay. I'd got some other way of doing the decimal stuff here, which was a slightly better way of doing this. So I was fiddling around in the decimal part. Let's see if how much difference that makes. I'll probably skip over that one. We've only got a few minutes left.
If you try Control L, it pushes up to the top of the screen and everyone can see.
Okay, sorry, that will, yes. Yeah, I'm sorry, I'm correct, sorry. I moved that one there so we could look at the cachegrind output. I didn't revert it, thank you. And what's that one going to give us in terms of, hey, yeah, okay, right, so we've now down to 1.25, we're doing quite well. So let's see what the next one after that might be. So I'd like to get into the last few of these ones here. So what do I do at that point? We can go through and have a look, but we're running out of time. So instead of this if field counter, blah, 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 and do the separator with the if statement and then print it out, I go, I'll print it out every time and then just do +1 at the end. I'm putting separator field, and then just not printing the first separator because I get rid of that if statement. I'm now down to the point where it starts to make a difference with the if statements inside loops, which is why I went from here to here. Let's very quickly take something like this and go to Compiler Explorer. So Compiler Explorer, for those of you who've probably seen most of this before, but so here is what Compiler Explorer makes of that particular piece of code there. It's not particularly good. You can see that the loop here has got a few extra instructions in this compare move. If I take that instead, go to here and put that as get string 2, we can compare that inner loop there, which is 1, 2, 3, 4, 5, 6, 7, 8 instructions, with an inner loop here, which is a smaller number of instructions. Which is 1, 2, 3, 4, 5, 6 instructions. So I've gone from 8 instructions in the inner loop to 6 instructions in the inner loop. Yes, we're down at that level. And I'll get on to 7. We're getting there. Right, okay. So if I start doing this kind of thing here, perf Oops, damn. Still got a lot of stuff going on here, unaligned and string length, etc. And I went, well, okay, looking this, I've got some system time here. Maybe I can deal with that. So let's have a look at and this is where, Michael, you've got to watch this one, Michael. Here we go, because then I say, well, look, input. Why am I doing all this read from input? I'm going to memory map the input. So I'm now using boost memory mapped I/O for the input instead of this one here. So this says, right, instead of having to do reads from things, I just map the file like this into memory and pass the data around and says, it's this much data, it's here. It's basically, it says, it's a big array. And then you just go, boom. So I can now do all that stuff with input and output here. It's just, I don't actually need to do anything here other than, right, okay, here's your input, here's your output, just take bytes from there, pick them up, process them, send them out again. That's what I got for this guy. Let's get the final one of this one here, because I'm a minute over. Sorry about that. Now, yes, I have to do -L. I'm now using a boost library, so I have to link with that. Bang! Now we're cooking on gas. Yeah, we're down from where are we? 1.09 down to 0.885. So I can go further than this one, but the next one is if you actually look at what those things are, you're going, at this point it is now worth doing unroll loops. So that's my final thing. Since I'm spending most of my time in there, if you do the profile, you find, look, it's all here. Let's unroll the loops. Yeah, so we're now down at the point where that we are hitting this one really quite hard. If you look at perf stat, you'll see this thing is now doing 2.67 instructions per cycle. Okay. It's got almost all of its branches correctly predicted. It's doing that one here, and so the total time of that one is, I'm now processing at about 220 megabytes a second, single-threaded on this laptop. Okay, so that's pretty much it. Fine. So just to say, we've had some tools. There's the optimization. Start with a simple, clear application. Avoid gross inefficiencies like lots of I/O. Lots of relentless measuring. Lots of tools. Learn to interpret the output of the tools and keep your code simple. Thank you very much. Are there any questions?